to my MT3 example video. Now on the previous ones I've written out the problem as I've gone, and I've struggled for time every time I've done that, so I'm just going to try to highlight things and stuff, plus my S Pen stopped working. So in this question, we're given a pressurized pipe, and you can think of, I guess there's some real world scenarios we can think of that this pipe could be in, where maybe it's a pressurized pipe underground and there's dirt sitting on it, or a bookshelf or something. And we can imagine how the stress and forces building up on the pipe would stack together. So first thing I did is, as usual, write out my given, give myself a really clear idea of what we're working with. I got my figure here, I've got my data points, I've got my Young's modulus and my ATS, ASS diameter, which I convert to radius later and all that. So what we're looking for is whether the pipe will fail. So something I did just mentally in my head was, I know just from experience, and I'm sure you do too, that when we see this distributed load, that we can do a resultant load in the middle, and we can imagine the pipe's going to bend in such a way that the maximum stress that we're going to be seeing is going to be at L/2, the maximum stress from bending at least, and it's going to be in compression on the top and in stress on the bottom. And so I just kind of wrote out, what that's going to look like when we add those pressures, that longitudinal and hoop stress. We know in the directions that it acts, we know that it's trying to push the caps off longitudinally, or rather it's just acting outwards if we imagine that it's an infinite pipe. And we know that the circumferential stress is like trying to tear it open. And anyone who's ever bursted a hose knows that hoses typically burst along their longitudinal direction, which is interesting when we think about it, because we know that hoop stress is greater than the longitudinal stress from the pressure itself. So it kind of makes sense when we think about the fact that that hoop stress is going to tear it along that normal plane to the hoop stress. And so just kind of working that out in my head, I just kind of wrote out how things are going to add together to help me think of what I need to find. Honestly, this principal min-max stress equation didn't really help me all that much. To be honest, I didn't end up using it really, but let's just keep moving along. So the first thing we want is the reactions. We know that we have AY, BY, we know there's technically a BX, and we know that there's a Q times L for that resultant distributed load on top. I did the sum of the forces in the Y, up direction is positive, and I wrote out my distributed load with AY plus BY equals 0. I wrote the distributed load as negative since it acts downwards. And then I solved for AY. I knew that I had to find BY as well, and so I did sum of the moments. And I took my moment about AY, and then I solved for BY, went back, plugged BY into my equation up here, and solved for AY. And that makes sense because we figure, well, if we've got a symmetrical load on top, we're probably going to be, our reaction forces will probably be about half of that total load on top, and that's what we see here, so that makes sense. Now, I shot myself in the foot here. For some reason, I'm just so used to doing it from the right. It's typically easier for me with most problems. This problem, that wasn't true, and since I thoughtlessly did my cut of the right side rather than the left, I kind of gave myself more work than I needed to. You'll notice that I had to work with this L minus X, so I was just introducing terms that I would have otherwise not had to have dealt with. But I trucked along, I kept going, and when I went and checked whether my answers were right, thankfully everything worked out. So that just kind of is a cool proof of concept that you can cut it on either side, but it would have been easier if I cut with the left side. I think I was trying to avoid the roller. Sometimes that's useful. In this problem, it wasn't really useful. So I did my sum of the moments in the y again. I have my internal forces using the internal force conventions. So it's the m's making the beam smile, the v is making it rotate clockwise. And I got my by plus v minus q l minus x equals 0. Solve for v. Kept everything as variables because it's just easier to write out that way. And let's see here. When you plug everything in too, you'll notice that since the v value is positive, we know that our assumed sense actually makes sense. And when we think about it, this is kind of just a smaller version of the thing we already saw before, so that makes sense. Some of the moments revealed a rather long m, and this is where I was saying that I really shot myself in the foot in terms of having to deal with the L minus X rather than just X. But it's okay because it worked out. And I know that my sigma b, so that's my stress from bending, is going to be my MYI. Sometimes I guess you could also write it as negative MC over I. You'll see it in that form sometimes. But here I just remember that when I give my radius as a positive, it's going to give me my compressive factor, and when I do my y as negative the radius, it's going to give me my tensile. And so I knew I needed to solve for I, so I took my outer radius, just did it here using the thickness. I did my outer radius times my thickness to get that inner radius, and so we know when we take the area of that big outer circle minus that smaller inner circle, and we take the moment of inertia about both of those, subtracting the smaller one from the bigger one, we get our resultant, and this is what I got. I wrote down my y just to remind myself that the positive and negative of this is what's going to give me my top and bottom stress from bending. I think here I was just showing that I did the compressive, and then I started going and solving for my circumferential stress from pressure as well as my longitudinal stress from the pressurized aspects of the problem. So pressurized forces are the stress resulting from that pressure. And so we would expect that circumferential hoop stress to be greater, which here it was 0.14 gigapascals or 140 megapascals. And then our longitudinal was about half that, which makes sense because we know that equation's PR over 2. So it's just going to be half of whatever the circumferential or hoop stress is. We know that's not the whole story, though. We know we want to add that. So this is where it gets kind of confusing. We know we want to add that to get our sigma 1 in that plane, the stress that's going on. We know on the bottom and the top it's going to be either additive or subtractive. And so we know, like, on top it's going to be, on top of the beam it's going to be like, it's going to be compressing up here, it's going to be in tension down here, and we know since that longitudinal stress from the pressure, it's going to add to that bottom tension, and it's going to kind of cancel out to some degree on that compressive side on the top. That said, we have to also be careful, though, the fact that we know that our principal tension, or our principal shear, is going to kind of come into play in a pretty interesting way in this problem. And so, let's see, for this sigma 1, I did that longitudinal plus the stress from bending. For the bottom, since I know on top it's going to be smaller, so I just concerned myself with the bottom. And so I got 1.4 e to the 8 pascals. For sigma 2, we know that in terms of tension, we can imagine it as tension. Oh my gosh, I wrote it so far down there. When we look at that hoop. And so Q max 140 megapascals, which is just relating to that answer up here. And so we know that that was in tension since it was on the bottom, as we showed there. And so 140 megapascals is less than the given 150, I believe, right? Yep, 150. Our ASS is 68, our ATS is 150. So we know that it's not going to fail in that regard from tension by itself. And so with our principal stresses, in order to find our shear max, we know that we can take that sigma 2 divided by 2 to get our principal shear as a result of our hoop stress, which is kind of weird to imagine, but if you imagine the top of that hoop, you know that that tension looks something like this, right? And you can imagine that there's a way that you could draw an element where it's being sheared, right? It's being sheared in some way, like, say like that, right? And so we know there's a way to acquire that, and so we acquire the max shear that is being caused from that hoop stress, and it ends up being about half of that 140 gigapascals. So that's 70, and 70 megapascals is greater than 68, and so it fails in shear. It's not easy drawing with a mouse, or with touch trackpad, sorry. And so it fails there, and then on top, we know that our longitudinal stress, let's see, oh wait, no, our hoop stress being 140 megapascals, if we imagine that as tension, as I drew here, so I guess if we, it's not really an easy way to draw this, if we imagine this is our element, and it's being stretched from that hoop stress, then we can just take that hoop stress directly and compare it to that 150 ATS, and we see that it's not going to fail due to that alone, due to the hoop stress alone acting as a tensile force, or a tensile, purely tensile stress. But once again, and I kind of drew out a drawing to help explain this as well as I can, we know that there's going to be a principal, our principal stresses are going to reveal a shear max. And so with that shear max, I did the hoop stress, and this one's really kind of hard to visualize, so I did my best to draw it out. We take that hoop stress and subtract the negative stress caused from bending, and so we end up with 70 megapascals, which is again greater than that 68 shear stress limit that we were imposed. And I kind of tried to draw it here, so you can kind of imagine there's the hoop stress, it's pushing an element perhaps in some way that it's squishing it, and we can imagine our stress from bending, and we can imagine that that's sort of like if the hoop stress is squishing something in one direction, maybe the bending stress is stretching it in another, and it's ultimately causing like this kind of intense shear stress on an element if you orient it a certain way in this plane.